So let's do an overall optimization review. First, let's do a second derivative test. And so when does the second derivative test, when do we think about applying? When you want to find local extrema. And sometimes it's inconclusive. And so one thing to consider is that all the second derivatives have to exist, and we like them to be also continuous. And then you set up the discriminant of x and y is going to be the fxx and x and y times fyy at x and y minus fxy. If the second derivatives are continuous, by Claire's theorem, it's going to be fxy and fyx are going to be the same, so you just write that to power 2. And so the discriminant, if discriminant is positive and separately you find a and b, you find the critical points a and b by setting the gradient vector equal to 0. That is the partial respect to x equal to 0, partial respect to y equal to 0. You solve and you get all the critical points that would work in the second derivative test, because those are the ones that actually give the partial equal to first partials equal to 0. Again, all I'm doing is going over functions of 2 variables, and then for a function of more than 2 variables, go back to your notes and check those out. And so if there are 2 conditions that give us information, either this is strictly bigger than 0, strictly less than 0, this one does not give any information. It can be anything. Inconclusive. Again, go back to the notes and see that it can be basically anything when that happens. And so there are examples in the lecture notes. And so when it's less than 0, then a and b is a saddle point. And so when the discriminant is bigger than 0, then if f sub xx of a and b is bigger than 0, 2 conditions. If it's bigger than 0, then we have a local minimum. If it's less than 0, we have a local maximum. And again, we discussed that if the discriminant is bigger than 0, then sign of f sub xx and f sub yy have to be the same. So it's just you check one of them, you don't check both of them, and that's the way that it goes. So this one is just to finding the local min, local max, or a saddle point, and it's not again equivalent to first derivative test is very difficult in calculus 3, and just basically best way to do it is use the numerical methods and stuff like that. So now method 2, that is the second method of optimization that we have, is closed and bounded region. This is basically equivalent to the closed and bounded interval in calculus 1. So what are the examples of closed and bounded regions? For example, this is a closed and bounded region, has boundary, are all in finite places, and then you can basically encircle them in a small in a finite circle, basically. And then, or it can be something like that, a disk. And so when the boundary is a disk, the next method that we discuss for checking the boundary is one of the best ones. When the boundary has multiple pieces, look, each piece of boundary here, the rectangle has 4 pieces, and each piece basically, or it could be a triangle also, each piece has its own elementary function, which is a line, basically elementary, which one way or another it can be an elementary function. It could be x function of y or y function of x, and so it's locally elementary. But then the entire thing is not, and I can't parameterize all of it at once. I have to parameterize piece by piece. But with a circle, I can parameterize the entire thing. So that's something to consider. And then so what happens in here, or I can give an equation of the circle for the whole thing. That's another thing to mention, and that makes the next method better for that. But anyway, what you do with any of these, if you just want to use what you learned in 14.7, is that you first find the critical points by setting gradient vector. Critical points. See if the critical point belongs inside this or in the boundary. If it doesn't, just throw them away. So keep the ones in the region. And then the next thing that you do is you parameterize each piece of the boundary, or in this case the entire boundary, and then you, when you parameterize, you get parameterize the boundary, and then each parameterization is a function of one variable. So now you parameterize the boundary. Each parameterization is a function of one variable, and you know how to optimize functions of one variable. Basically, it's like using, in this case, using 4 closed interval method in calculus 1. So you find maximal critical values in here, here, but don't find the y value, because you have to find the z value in here instead of y value, right? Don't find it for each piece. What you do, you use this to find critical points on the boundary. Then set what you found in 1 and 2 plus all the corner points, like end points. So for example, these are the endpoints here, these are the endpoints in here, and plus the endpoints. Compare z. So the maximum z is going to be the maximum, the absolute maximum over the region. The minimum z is going to be the minimum z in the region, basically, of the minimum z of the, that's the absolute minimum over the region. Now, what is the Lagrange multiplier? Lagrange multiplier, again, there is the function that you're optimizing, but this time there's a constraint. Instead of giving it's the bounded region, for example, it gives you a constraint. The constraint can be the circle around here, or it could be that, or it could be this. just the basically it would be a one-dimensional curve or that sort of thing. So the boundary of those can count, or other type of constraints basically. And then what you do is, this is the interesting part, you find the gradient of f, then you set it equal to, we use lambda because lambda is not used anywhere else, it's just a constant, times gradient of g. And so basically you take the partial of f respect to x, you set it equal to lambda partial of g respect to x, and pick a partial of f respect to y, set it equal to lambda partial of g respect to y. That is, the two gradients are supposed to be parallel. Okay, so this gives you, for a function of two variable, this gives you two equations. Then you set the third equation is the constraint. And then you solve, the best way is to eliminate lambda in these two equations, and then you have an equation of x and y, and then you have another equation of x and y, and then you eliminate x to find y, or eliminate y to find x, and then basically solve for the other variable. And then you find the x and y that, or a and b, such that a and b is the critical value, the critical value for the constraint. So with the Lagrange multipliers, you either have to make sure that the constraint is bounded and closed, like it's just a boundary like that, or this or that, or you have to know by other piece of information, sometimes by experience, that there's a local max, or there's absolute max or absolute min that happens according to the problem. And then if you check all the points that you get from here, sometimes more than one point, and basically if all the conditions are right and closed and bounded constraint is happening, then you get at least 2. And so in that case, you check them and see what is maximum is going to be the maximum on the constraint, and what is minimum is going to be minimum in constraint. So when I'm saying this can replace part of this problem, is that part, the parameterization and stuff, can be replaced by this part. And so sometimes this is easier, sometimes that is easier. We usually separate the two for exam type of questions. But the interesting part is that in real life, you should kind of try them all to see which one works for the situation that you're dealing with. And a lot of basically business stuff goes with this, because you have multiple conditions that affects your business, and multiple all sort of things. And so this type of problem comes up a lot, and it gives you a bunch of ways of solving it basically.